Okay, welcome back. Dr. Pitcher here again. And in this lecture, we'll take a look at our first real reaction of the semester, which is the electrophilic addition reactions of alkenes. In particular, let's look at the addition of a hydrohalide to a carbon-carbon double bond. And we could do any hydrohalide. I'm going to use HBr to a C double bond. So when the text talks about electrophilic addition, it means that it's an electrophile that's being added to the double bond. So the double bond is acting as a nucleophile. So for example, we could take a look at the following compound here, 2-methylpropene, and we could react it with HBr, and we will go ahead and get as our product H3C, CH3, Br, CH3. So in this case, the bromine is ending up adding onto this carbon, and the hydrogen is adding there. So maybe I should write it out as follows. H3C, CH3, double bond CH, plus HBr. And that gives us now H3C, CH3, CH. And that's what we end up with. The bromine is added to one carbon in the double bond, and the hydrogen is added to the other carbon. Now, the question is, how does this happen? The answer to that is the mechanism. And what happens, or the mechanism that is consistent with experimental observations, and we'll talk more about that a little bit later. What happens is the following. We've got H3C, H3, double bond C, H, plus HBr. Draw in my lone pairs. The first thing that happens is we are going to pick up the proton. So a pair of electrons from the double bond plucks that proton off of the HBr. And now my electrons from that HBr bond go on to the bromine. And that is going to give us the following. So this is a carbocation intermediate. And then we still have our bromine, and now it's Br minus, because it got that got the electrons from that bond. And now this can go ahead and now add to the carbocation, giving us our final product. And I'm just showing these hydrogens or writing them out because that's what I had done here. So we can look at this in a few different ways. This is, of course, our curved arrow notation, and you guys will want to get good at drawing these. And you know, as we go along, I'll explain mechanisms. But a typical mechanism type problem, you would have a reaction and be asked to write the mechanism. So you'd have to propose a series of steps that make sense. So looking at this, what do we have? Well, again, first we have the protonation of our alkene. So pi electrons from the double bond pull the proton off. So they reach out and they pluck the proton off. And that proton happens to go to this carbon, the less substituted carbon. We'll talk about that in just a minute. And that gives us this carbocation intermediate, and then the negative bromine is now going to be the nucleophile. Now this is the electrophile, and we can get nucleophilic attack. So here our alkene is our nucleophile, and our hydrogen here from HBr is the electrophile. Anyway, and that gets us to where we need to go. So when you're dealing with a mechanism problem, you know where you have to end up, and what you have to provide is a series of steps to get there. So you'll want to start thinking about, you know, okay, what happens in these reactions? How do they occur? And then we'll take a look at how evidence for how we know these reactions occur. It turns out that you can't conclusively prove 100% that a particular mechanism is the correct mechanism. You know, you can do 99.99%. You can disprove a mechanism, but you know, your mechanism should be consistent with data. I wanted to show you this energy diagram from the text. I didn't want to recreate it. And it just shows what's going on here. This is a two-step mechanism. So first step, second step. And in the first step, we have the proton transfer, and that makes our carbocation intermediate. And then in the second step, we have the nucleophilic attack from the bromine on the carbocation. So this first step has the bigger activation energy. Here it's called delta G double dagger, but we call it EA. So let me call this EA1. And this is EA2 there. And so that's going to be our rate determining step. Now we could add other things. We could add HCl. We could use some other, instead of using HI, we use this combination of Ki and phosphoric acid. We could even add H2O. In the form of water and then an acid catalyst. And so we add OH on one side and then an H on the other side. So just to add in here, I'll have an H there, and you know, here I started with one hydrogen, and so now I've got two. So I've added my OH and my H. Okay, so that's what's going on with these types of reactions, and the addition of HBr is a particular type of electrophilic addition to alkenes. There is an aspect of this that I do want to talk about in a little more detail. Let me zoom out again. Sorry about that. There is an aspect that I do want to just talk a little bit more about, and that's the following. So when we do this reaction, And we'll look here at, I'm going to call this the regiochemistry of electrophilic addition of alkenes. Sorry about that. Let me just tidy that up a bit. There we go. So again, if I have my if I have my addition of HBr to my 2-methylpropene, I get 2-butyl bromide. Okay, I don't get this species here where the bromine adds to the end. Remember when I mentioned in, actually it was in short lab when I was talking about drawing curved arrows, giving a little just a little reminder, a little curved arrow pep talk. You know, we drew our curved arrow here, and I said, yeah, you have to determine which carbon gets the hydrogen. And so it turns out that there are some rules for this, and we see that in the addition of HBr to 2-methylpropene, we only get the T-butyl bromide, the 2-bromo 2-methylpropane. We don't get the 1-bromo 2-methylpropane. So why is that? Well, the explanation given is something called Markovnikov's rule. And I'm going to give you the original version. So Markovnikov's rule in the original version said that when you're adding HX to an alkene, the H attaches to the carbon with fewer substituents. And of course that means that, and the X attaches to the carbon with more substituents. So our H goes to the less substituted carbon, and the X, in this case X is bromine, goes to the more substituted carbon. The question is why? Why does that happen? Well, let's take a look. I mean, this describes what's going on, but why? Well, let's look at the mechanism again. So I'm going to draw it two ways here. So I'm going to have my, let's see, carbon, CH3, CH3, CHH, plus HBr, and then a different color here. H3C, C, CH3, plus HBr. Now, we've already seen this mechanism, so I'll just go ahead and draw it out here real quick. We get our deprotonation, or rather our proton transfer, I should say. And now I've got H3C, C, CH3, C, H, plus Br minus. Okay, so in this case, I'm adding my hydrogen to the less substituted carbon. And what that results in is the T-butyl bromide product. Just scooch that down, that product, the one that we actually see. So let's try to come up with a mechanism so that we get the other product. So the first step is going to look the same. It's going to be drawn the same, except now let's take let's do this. So CH3. We'll go ahead and put the hydrogen there, and then CH, positive charge. So now I'm adding my hydrogen to the more substituted. Of course, I'm going to have my bromine, bromide ion, I should say, and that can go ahead and add in, giving us H3C, C, CH3, H, C, H, Br. And this is the product that we actually don't see. So, you know, the question is, well, why don't we see this? Well, the answer lies in the actual mechanisms and the reaction pathways. And so what we see is the more stable carbocation is the one that forms. Okay, so let's take a look at this. I can actually draw this out here. If we look at our energy, if we look at an energy diagram here, a reaction, we'll have energy, and then we'll start with our you know, wherever we're starting here. So this is this guy plus HBr, and then we'll go ahead and do our addition, and this is just, it's basically figure, I think it was what, figure 7.7. I'll just double check that here, hold on. Figure 7.9. But now I'm going to add in what the energy would look like for the other one. So let me just draw in here. This is our carbocation like that. Now the other one, it turns out, has a much higher energy for its intermediate, which was that guy there, and then it ends up getting giving us, I don't know what the final energy is, but it's probably pretty similar here. So let me just draw that there. Maybe slightly higher in energy. But the key here is that we have a difference in our stability of our intermediate. And that stability is due to the type of carbocation. This carbocation, where we have, where is it? Here we go. Where we have a carbon attached to 3 other carbons, we call that a tertiary carbocation. Sometimes abbreviated 3 with a little degree sign. This carbocation, we have a carbon attached to just 1 other carbon. We call that primary. Which we could write or abbreviate as a 1 with a degree sign. And so the reason why we get this product and not the other one is because the tertiary carbocation is much more stable than the primary carbocation. It would take a lot more energy to make that primary carbocation, so the tertiary is going to be the one that actually forms. So you should, let's say, familiarize yourselves with the general trend in carbocation stability. And I think we'll talk about that in the next lecture. So until next time, stay safe out there and make sure you're drawing your curved arrows correctly. All right. Bye now.